This is lecture 5. This week we're going to cover lines, planes, and projections. First, let's talk about lines. To describe a line in three-dimensional space in R3, we need two things. We need a point, P0, that the line passes through, and we need a vector which gives the direction of the line. For example, if we let the vector R0 be the vector with initial point O and terminal point P0, and then we let the vector R be the vector with initial point the origin and terminal point P, then we can say that the line passing through the point P0 parallel to V has the vector equation R is equal to R0 plus TV. In coordinates, that's the same as x, y, z is equal to x0, y0, z0 plus t, v1, v2, v3. Or we can separate that into three equations. X is equal to x0 plus t v1, y is equal to y0 plus t v2, and z is equal to z0 t v3. And in practice, these are the ones we're going to be using. These are called parametric equations for the line L, which passes through the point P0 parallel to the vector V. For example, find parametric equations for the line passing through the point -2, 0, 4, parallel to the vector 2i plus 4j minus 2k. So we have our point -2, 0, 4. -2 goes at the start of the x equation, 0 goes at the start of the y equation, and 4 goes at the start of the z equation. And then we use our vector. 2i, so in the first equation we have 2t. 4j, so in the second equation we have 4j, and then minus 2k, so in the z equation we have minus 2t. And that line looks like this. We can see that the line passes through the point -2, 0, 4, and it passes through this when t is equal to 0. We can also see that the line, this blue line, is parallel to the orange vector. But all of the points along the line correspond to different values of t. For example, I've drawn the point when t is equal to half, when t is equal to 1, and the point when t is equal to 3/2. Find parametric equations for the line passing through the point P and the point Q. Now, this time we have 2 points, but we don't have a vector. But we can get a vector just by doing the vector from P to Q. We need a point and a vector, but we have 2 points. Which one do we use? It doesn't matter. We could choose to use P or we could choose to use Q. It really doesn't matter. I'm going to choose to use P in this answer. So choose P0 as P and choose V be the vector from P to Q. And then we do what we did before. The point, -3 to -3, write those down first. And then the vector, 4 -3 plus 7, so that gives us 4t minus 3t plus 7t. Now, previously we were saying t could be any real number, but let's suppose we want to restrict t to be in a closed interval. Then instead of an infinite line, which goes to infinity in either direction, we would have a line segment. For example, parameterize the line segment joining P and Q. Parameterize means find the parametric equations. Now, this is the same P and Q that we did in the previous example. So we know our x, y, and z equations. We just need to find the a and the b. We need to find where the ends of the line are using these equations. Note that if t is equal to 0, then we get p. We always get p if we do t equal to 0 because it's going to be minus 3 plus 0, 2 plus 0, minus 3 plus 0. And minus 3, 2, minus 3 is the coordinates of p. And also note, if we put t equal to 1 in, then it's going to be minus 3 plus 4, which is 1. 2 minus 3, minus 1, and minus 3 plus 7, which is 4. If we put t equal to 1 in, then we get q. Why is it 1? Because we used the vector from p to q. So the answer to this question is the same x, y, z equations, but because it's a line segment, we want t to be only between 0 and 1. And that looks like this. This is the line segment from P to Q. The distance from a point to a line. Let's suppose I have my blue line here, L, and I have my point S. I want to know what is the distance from F, the distance D from S to the line, the shortest possible distance from S to the line. Now, you can see from this diagram using trigonometry that D is the norm or the length of the vector PS multiplied by sine theta. But remember from last week, PS cross V is the same as norm of PS, norm of V, sine theta, and then the unit vector n. We take the norm of this vector, then the n will disappear because it's a unit vector, norm of a unit vector is equal to 1. Rearrange that and we get our formula. Distance from a point to a line is the norm of PS cross V divided by the norm of V. So for example, find the distance from the point 115 to the line 1 plus t, 3 minus t, 2t. We need a point on the line and we need a vector which is parallel to the line. To get the point, we use the first number, so 1, 3, and then the first number in the z equation would be 0, because the z equation we can think of as 0 plus 2t. So that's 1, 3, 0. And then for the vector, we use the second numbers. So that's plus 1t, minus 1t, plus 2t. So 1 minus 1, 2. We need the vector from P to S, so we can calculate that, minus 2j plus 5k. And then we need the cross product between PS and V. I'll leave it for you to check that this is I plus 5j plus 2k. And then we use our formula, the formula from the previous page. Distance from the point to the line is the norm of PS cross V divided by norm of V. Put our vectors in, calculate their norms, and we get our answer. Next, let's talk about intersecting lines. If you're using the Thomas's Calculus textbook, which I recommended, this section is not in the book. Two lines intersect at a point P if and only if P lies on both lines. So for example, do the following two lines intersect? And if the answer is yes, then where do they intersect? Now, we can say these two lines intersect if and only if we can find S and T. I should point out, by the way, because I've used T in the first line and because I don't want there to be any confusion, I'm using a different letter on the second line. So this is why it's T on the first line and S on the second line. These two lines intersect if and only if we can find these numbers S and T such that all three of these equations are true. X is 7 minus t and x is minus 1 plus 2t. Y is 3 plus 3t and y is equal to 3s. Z is equal to 2t and z is equal to 1 plus s. From the first one, rearrange it. We can see that we must have t is equal to 8 minus 2s. And then I want to put that into the then I want to look at the second equation. The second equation simplifies to s is equal to t plus 1. If we put the first equation into the second one, in other words, if we replace t plus 1 by 8 minus 2s plus 1, we get 9 minus 2s, and the solution of that is s is equal to 3. After we know s, we know that t must be 2. So if s is 3 and t is 2, then the first two equations are true. But that's not good enough. We need all three equations to be true at the same time. So the question is the third equation also true? We need to check the third equation. If we put t equal to 2, then we get 2t is equal to 2 by 2 is 4. If we put s is equal to 3, then 1 plus s is also equal to 4. So the answer is yes. S equal to 3 and t equal to 2 solves all three equations at the same time. Because all three equations are true at the same time, we know that the two lines intersect when s is 3 and t is 2. And by putting either t equal to 2 into the first line or s equal to 3 into the second line, we find the point where they intersect. They must intersect when x is equal to 5, y is equal to 9, and z is equal to 4. Let's do another one. Do these two lines intersect? And if the answer is yes, where? So we start with our three equations. We need x to be 1 plus t and x is equal to minus 1 plus 2s. We need 3t to be equal to 3s. We need 3 plus 3t to be equal to 1 plus s. Can we find s and t so that all three equations are true at the same time? Second equation, first of all, looks the easiest, so let's start with that one. Second equation says s is equal to t. If we put that into the first equation, we find that t must be 2, and so therefore s must be 2 as well. Does that also satisfy the third equation? The third equation, if s is equal to t, implies that t is equal to minus 2, which is not 2. That means it's not possible to find an s and t so that all three equations are true at the same time. And that then implies that the lines do not intersect. Let's talk about the distance between two lines. And again, this is not in the Thomas's calculus textbook. There's three cases to consider. Either we have intersecting lines, or we have parallel lines, or we have two lines which do not intersect and they're not parallel. We call these skew lines. And I've tried to draw this in this way. You should imagine that the blue line is somehow higher up than the red line. If the lines do not intersect and they're parallel, that means the vector v1 from the first line, it must be some number k multiplied by vector v2 for the second line. And if the lines do not intersect and are skew, that's the same as saying v1 is not equal to kv2 for any number k. The first one's the easiest one. If two lines intersect, then that means they touch, so the distance between them must be 0. What about parallel lines? Well, the distance between two parallel lines must be the same as distance from some point P2 on line 2 and line 1. And we know how to do that. We know how to do the distance from a point to a line. We'll just adapt our previous formula. The distance between parallel lines must be the norm of P1, P2 cross V1 divided by V1. Or if you want to, you could replace the vector V1 by V2 in this equation, and it will still be true. For skew lines, looking at this picture, if Q1 is the point on the first line which is closest to L2, and if Q2 is the point on L2 which is closest to L1, then we're trying to find the distance between Q1 and Q2. And of course, the two angles that I've drawn here are 90 degrees if the distance is the shortest possible distance. Because this line, this dotted line here, is orthogonal or perpendicular to both lines, we need to find a normal vector which is orthogonal to both V1 and V2. But we know how to do that. We know that if we take the cross product of V1 and V2, then we get a vector which is orthogonal to both V1 and V2. So this normal vector n must be parallel to the dotted line. What is the distance from Q1 to Q2? It's the same as the norm of the vector P1, P2 projected onto n. It's the same as the part of the vector from P1 to P2, which goes from line 1 to line 2, but projected, or the part of it which is in the same direction as n. And we've talked about that last week. We have a formula for the projection of a vector onto a vector. That's absolute value of P1, P2 dot n divided by the norm of n. So that gives us our formula. You don't necessarily have to understand the derivation of this formula, but remember this formula, you would need to use this formula. So let's just recap this. The distance between two intersecting lines is 0. The distance between two parallel lines, we have our formula. Norm of P1, P2 cross V1 divided by norm of V1. And the distance between skew lines, absolute value of P1, P2 dot V1 cross V2 divided by the norm of V1, V2. And there's one little bit of more information before I continue. We know we have parallel lines if we have lines which do not intersect and which V1 cross V2 is the 0 vector. And we know we have skew lines if we know that the two lines do not intersect and V1 cross V2 is not the 0 vector. So let's do some examples. Find the distance between the following two lines. And I can tell you that these lines do not intersect. So we either have parallel or we have skew lines. So the first thing to do is to ask, are they parallel or are they skew? And we answer that by calculating V1 cross V2. But I'm getting ahead of myself. We need a point on line 1. So if we set t equal to 0 in the first equations, we get 0, 0, 0. And we also need a vector which is parallel to line 1. We look at the numbers in front of the t. So 0t minus 1t plus 1t gives us 0i minus 1j plus 1k. And then we do the same thing for the second line. If we put s equal to 0, we get 1, 0, 0. And if we look at the numbers in front of the s terms, we get 2, 1, minus 3. We need to do the cross product of these two vectors, and I'll leave it for you to check that we get 2i plus 2j plus 2k, which is not the 0 vector. So we do not have parallel lines, we have skew lines. So now we know which formula to use. We're going to use the formula for skew lines. put all the information in, and I'll leave this for you to check the calculations. Check that the answer is 1 over root 3. So to recap, to answer a question like this, first we need a point on each line and we need a vector parallel to each line. And then we do their cross product to find out if the lines are parallel or skewed. And that tells us which formula to use. And then the second half of the problem is just using the formula to calculate the answer. Our second chapter for today is a chapter about planes. To describe a plane, we also need two things, but this time we need a point on the plane, a point P0, and we need a vector which is perpendicular to the plane. The perpendicular vector n is said to be normal to the plane. The plane passing through the point P0 with normal vector n has the vector equation n dot P0P is equal to the number 0. Why? Because this angle here is 90 degrees. If the angle between two vectors is 90 degrees, then that means their dot product is equal to 0. In terms of coordinates, that's the same as ax minus x0 plus by minus y0 plus cz minus z0 is equal to 0. Or we could rearrange that to ax plus by plus cz is equal to d for a different number d. And it's this formula in the box which is the one we're going to be using. For example, find an equation for the plane passing through the point minus 3, 0, 7, normal to the vector 5i plus 2j minus k. So I'm starting with the first formula, first coordinate formula of the previous slide, and I want to end up with something that looks like the one in the box. I'm starting with ax minus x0 plus by minus y0 plus cz minus z0 is equal to 0. Put the numbers in and then rearrange, and we get our answer. Our answer is 5x plus 2y minus z is equal to minus 22. Let me just remark that the vector ai plus pj plus ck is normal to the plane ax plus by plus cz is equal to d. So anytime we're told a normal vector, immediately we know what the left side of the plane equation is going to be. It's always going to be ax plus by plus cz is equal to some number. In the previous example, the calculation was just to find the number d. Or going the other way, if we're told a plane equation, we can just read off the numbers a, b, c, and then we'll know straight away the normal vector. So for example, find a vector normal to the plane, x plus 2y plus 3z is equal to 4. The numbers here are 1, 2, and 3. So straight away, we can immediately write down that the normal vector is I plus 2j plus 3k. Another example, find an equation for the plane containing the points 0, 0, 1, 2, 0, 0, and 0, 3, 0. We need to find a normal vector first. We need to find a vector n which is orthogonal to both the vector ef and the vector eg. And how do we do that? If we have two vectors and we want to find a vector which is orthogonal to both of them, we just take their cross product. So we want the vector ef cross eg. And I'll leave this calculation for you to check. You can check that ef cross eg is 3i plus 2j plus 6k. So straight away we know that the answer to this question is going to be 3x plus 2y plus 6z is equal to some number. If we use, we need a point on the plane, we could choose any of these 3 points. Let's say we choose E. If we choose E, the point 0, 0, 1, then we can do our calculation and we can find that the answer to this question is 3x plus 2y plus 6z is equal to 6. Let's talk about lines of intersection. Two planes are parallel if and only if the normal vector of one plane is just a number multiplied the normal vector of the other plane. And they're not parallel, that means they intersect in a line. Assuming they're different planes, they intersect in a line if and only if n1 is not equal to some number k n2 for any number k. Let's look at the green line in this picture, the line of intersection between the two planes. A vector parallel to the green line is orthogonal to n1 and it's orthogonal to n2. How do we get a vector which is orthogonal to both n1 and n2? We do n1 cross n2. So for example, find a vector parallel to the line of intersection of these two planes. We're going to write down the two normal vectors and then we're going to take their cross product. Just by looking at the formulae for the planes, we can immediately write down the normal vectors. For the first one, the numbers are 3, -6, and -2. So the first normal vector is going to be 3i minus 6j minus 2k. If we do their cross product, and I leave this for you to check, we get the answer to this question. Find the point where this line intersects this plane. So we have a plane and we have a line, and we're trying to find the point where the line intersects or passes through the plane. So we're going to do the calculation like this. We're going to start with the equation for the plane. 3x plus 2y plus 6z is equal to 6. But we know that x is 8 over 3 plus 2t. We know that y is minus 2t. And we know that z is 1 plus t. So we're going to put these in instead. So 3 times 8 over 3 plus 6t plus 2 times minus 2t plus 6 times 1 plus t is equal to 6. And then we're going to rearrange this and simplify it until we end up with t is equal to -1. As soon as we know t, we can put that into the equation of the line and we can find x, y, and z. The point of intersection is the point x, y, z when t is equal to -1. So that's 8 over 3 plus 2t, minus 2t, 1 plus t, but with t equal to -1. So 2 over 3, comma 2, comma 0. The distance from a point to a plane. In this picture, we're trying to find d, the distance from the point S to the plane, the shortest possible distance from the point S to the plane. And we can see from the right-hand side that the dashed line D is parallel to the projection of PS onto N. If it's not just parallel, it has the same length as the projection of PS onto N. So D must be equal to the norm of the projection of PS over N. So therefore, the distance from point S to a plane N, we have our formula because we know how to do projection of a vector onto vector. The formula is the absolute value of PS dot N divided by the norm of N. Find the distance from the point 1, 2, 3 to the plane x plus 2y plus 3z is equal to 4. I've put the formula we're going to use at the top in the yellow box. But first, we need to find a point on the plane. We need to find some point which satisfies x plus 2y plus 3z is equal to 4. Now, of course, there's infinitely many points on the plane. We only need to find one of them, any one point on the plane. And to make it easier for ourselves, we could say, let's let two of these numbers be 0. For example, we could have, let's say, y is 0 and z is 0. We could choose any two of the numbers to be 0. I'm choosing to use y and z. After we've chosen y and z as 0, then we can see we have x plus 0 is equal to 4. So x must be equal to 4. So therefore, 4, 0, 0 we need a vector which is normal to the plane. That's easy. Just looking at the equation, we can immediately see that the numbers are 1, 2, and 3. So n is I plus 2j plus 3k. And we need the vector from P to S. That's minus 3i plus 2j plus 3k. Put everything we have into the formula and calculate the answer, and I'll leave that for you to check. If I haven't made a mistake, and please check this for me, the answer should be 10 over root 14. Let's talk about the angle between two planes. There's two possible angles between two planes, as you can see from this picture. We are interested in the smaller angle. So in particular, or more precisely, the angle between two planes is defined to be equal to whichever of the following angles is smaller. The angle between n1 and n2, or 180 degrees minus the angle between n1 and n2. So that means that the angle between two planes will always be between 0 degrees and 90 degrees. For example, find the angle between these two planes. We need to write down the two normal vectors. We're going to calculate the angle between the two normal vectors. And if that angle is bigger than 90 degrees, then we'll do 180 minus that angle. First part is easy. We can immediately write down the two normal vectors. And then we had our formula from last week about the angle between two vectors, and we can calculate that it's approximately 101 degrees. But 101 degrees is bigger than 90 degrees. So we're going to do 180 minus 101, and to get the answer, approximately 79 degrees. Our final projection, our final chapter for this week is projections. Now, last week we defined the projection of a vector u onto a vector b to be given by this formula. I want to extend this idea this week. The first type of projection we're going to talk about is the projection of a vector onto a line. Let L be the line passing through the point P in the direction V. Well, we can say that the projection of a vector u onto a line L is the same as the projection of a vector u onto a vector v. We can see that from the picture, and we have that formula. So, for example, find the projection of the vector u onto this line. Clearly, v is 2i minus j minus 4k, so really what we're doing is the projection of u onto v. And I'll skip the details here because this is just repeating what we did last week. Or we could do the projection of a vector onto a plane. Here's the picture. We have some vector u, and I want to project this onto this blue plane. Two ways to think about it. Either we can think that we're going to push down from the top, and we're going to squash the red vector down onto the blue plane. Or we can think about this another way. We can think that there's a sun up at the top, and we're looking for the shadow of the red vector onto the plane. Now, in this picture, we can see that green vector plus orange vector is equal to red vector. Because of the way we add vectors together, if they're nose to tail, green plus orange is equal to red. And that gives us our definition. The projection of a vector u onto a plane with normal vector n is just u minus the projection of u onto the normal vector n. Let's do an example using this formula. Find the projection of the vector u onto the plane 3x minus y plus 2z is equal to 7. Clearly, our normal vector n is 3i minus j plus 2k. We want to calculate the projection of u onto n. Check the details for me. And then, using our new formula, the projection of u onto the plane is going to be u minus the projection of u onto n. Again, check the details for me. Make sure I didn't make a mistake. I think it's minus a half I plus 5 over 2j plus 2k. The projection of a point onto a plane. So suppose we have our point P, and we want to either squash this down onto the plane, or if there's a sun up here, we're looking for the shadow of the point P onto the plane. Now we can see from this picture that if we started at the point P, and then if we did the orange vector, we would end up at the projection of P onto the plane. So that's exactly what we do. The projection of the point P onto the plane is the point P plus the projection of the vector PQ onto the vector n. For example, find the projection of point 1, 2, minus 4 onto the plane. 2x plus y plus 4z is equal to 2. Two things. First, we need the projection of PQ onto n. You can check the details for me here. I'm being deliberately quick. And then using our new formula, the one we want, projection of P onto the plane, is equal to P plus the projection of PQ onto n. And that's just adding two vectors together to get the answer. Now, wait a minute. We should check our answer here to make sure that we haven't made a mistake. And the way we can check it is we can check that if the point 7, 3, 8, 3, minus 4, 3 really is on this plane. So what we can do is we replace x by 7 over 3. We can replace y by 8 over 3. We can replace z by minus 4 over 3. And then the question is, do we really get 2 or do we get a different number? And this time, we do get 2. So we almost certainly didn't make a mistake in our calculation. The projection of a line onto a plane. Let's suppose we have a line L which passes through a point P in the direction of V. Let's suppose we have a plane with normal vector AI plus PJ plus CK. Then there's three cases that we should be considering. Case number 1. The line is orthogonal to the plane. So if I draw a quick picture, here's my plane. And my line goes like this, where we have a 90-degree angle between the line and the plane. We know we have this case if V cross n is equal to the 0 vector. The second case we're going to be considering is the case where the line is parallel to the plane. So again, here's my plane, and here's my line. Now remember, here's the vector v, and here's the vector n. We know that we have a line parallel to a plane if these two vectors are orthogonal. In other words, if their dot product is the number 0. And then the third case to consider is the case when the line is not parallel to the plane and it's not orthogonal to the plane. So in other words, if we have something like this, we have a line passing through a plane and the angle between the line and the plane is not 90 degrees. We know we're in this situation if v dot n is not the number 0 and v cross n is not the 0 vector. So, first case. If we have a line orthogonal to the planes, if v cross n is the 0 vector, this is the easiest case because the projection of a line onto a plane, and remember, projection means we're just going to squash everything. We're going to squash from the top and the bottom, and we're just going to squash the line onto the plane. Or, to say it another way, we're looking for the shadow of the line onto the plane. It's just going to be the point where the line intersects the plane. And we know how to find the intersection between a point and a plane. Case 2, the case where the line is parallel to the plane. The black line here is the projection of the line onto the plane. It's the shadow of the line, or it's if we squash the line down or push the line down onto the plane. We can see that this black line passes through the point, projection of P onto the plane, and because the red line and the black line are parallel, that means that it must have the same parallel vector V. And case 3, a line which is neither parallel to nor orthogonal to the plane. This time we're going to find 2 points on the new line, and then we know how to find the line passing through 2 points. The point B is the point where the line intersects the plane. We know how to do that. And we'll have another point by doing the projection of some point P onto the plane. And then we'll be finding the line passing through these 2 points. So, for example, find the projection of this line onto this plane. Step 1, find V and N. That's straightforward. We can write those down just by looking at the formula in the question. And then step 2, does the line intersect the plane? We do V dot N, and this is not 0. That tells us that the line is not parallel to the plane, therefore it does intersect the plane. So we have either that the line is orthogonal to the plane, or the line is not parallel and not orthogonal to the plane. One of these cases must be true. Step 3, let's find the point of intersection. We do the same thing that we did earlier. Start with the equation of the plane, replace x by 7 plus 60 plus y by minus 3 plus 15, and replace z by 10 minus 2t. Simplify it down until you get to t equal to 2 over 5, and then calculate the coordinates of the point x, y, 0 when t is equal to 2 over 5. We'll come back to that later, but first, is the line orthogonal to the plane? To answer this question, we need the cross product of v and n, and we find the answer is equal to the 0 vector. So the answer is yes. The line is orthogonal to the plane. We know we have this situation with a 90-degree angle, and we know the coordinates of the point where the line intersects the plane. And that's just the projection of the line onto the plane. The projection of the line onto the plane is just the point where the line intersects the plane. So the answer to this question is the point 9.4, 3, 5.2. Let's do another example. Find the projection of this line onto this plane. Start the same way, find V and N, and then answer the question, does the line intersect the plane? To answer that, we do V dot N, and this time we get the 0 vector. That tells us that the line does not intersect the plane. The line is parallel to the plane. So we want a new line which has the same vector V. We just need to find a point on the new line. As soon as we find a point on the new line, we can write down the equation of the new line. So, step 3, find a point on the projection of the line onto the plane. The point 1, 2, 3 lies on the original line, and the point 9, 0, 0 lies on the plane. I took the equation of a plane, I put y equal to 0 and z equal to 0, and then I saw I must have x is equal to 9. So what I do is I do the vector pq, and I project this onto n, and then I add this onto p to get the projection of the p onto the plane. It's p plus the projection of pq onto n to get 5/2, 4 minus half. Now, at this point, let's just do a quick double check that we haven't made any mistakes in our calculation. Does this point really lie on the plane? We'll put it into the equation. We'll start with 3x plus 4y minus 7z. Replace x by 5/2, y by 4, and z by minus half. Do we really get 27? The answer is yes. So far, no mistakes. Let's move on. Part 4, the final part, find the projection of L onto the plane. We want the line which passes through the point 5/2, 4 minus a half, and it has the same direction as the line that we started with. So it still has direction 4i plus 4j plus 4k. And as soon as we know the point on the line and a parallel vector, straight away we can write down the answer. 5/2 plus 40, 4 plus 40, minus a half plus 40. One more example, final example for today's lesson. Find the projection of this line onto this plane. Step 1 and step 2 are the same as before. Find V and N, and then answer the question, does the line intersect the plane? We calculate the dot product between V and N, and we find something which is not 0. That tells us that we do intersect the plane. So now we know either we're in the orthogonal case or we're in the case which is not orthogonal. Step 3, find the point where the line intersects the plane. I'll leave this for you to check. It's the same type of calculation we've done before. Check that the answer is 0, 3, 6. And then step 4, is the line orthogonal to the plane? We answer that by doing V cross N, and this time we do not get the 0 vector, which tells us the line is not orthogonal to the plane. So now we know that the picture looks something like this. Angle between the line and the plane is not 90 degrees. We know the point where the lines intersect. That point must also be on the new line. We need to find another point on the new line. So what we're going to do is take a point on the original line and then project it down onto the plane, and then we'll find the line passing through those 2 points. So find another point on the projection of the line onto a plane. The point 15 minus 12, 17 lies on the original line. So the vector PB points from this point to the plane. Project this onto N, and then add that onto P, and we get the point 2, minus 3, 1. That should be another point which is on the new line. There's another point on the projection of the line onto the plane. Of course, if we have time, we should do a quick check. Is this point really on the plane? I'll leave that for you to do. The final step is then to find the projection of the line onto the plane. We want the line which passes through B and this new point that we found, the projection of P onto the plane. So we want the vector which passes from B to this new point, projection of P onto the plane. We can calculate that. And then the answer to this question is the line passing through B in the direction V2. And you know how to do that. Straight away, we can write down the answer to the final example of this week's lesson is x is equal to 2t, y is equal to 3 minus 6t, z is equal to 6 minus 5t. And that is the end of this week's video. And that's also the end of our study of geometry. Next time, we're going to be talking about combinatorics, which is a fancy way of saying counting. And then we're going to start talking about probability. If you have any questions, feel free to ask me in the discussion board.